Mathematical induction divisibility proofs. Mathematical induction divisibility can be used to prove divisibility, such as divisible by 3, 5, etc. Same as mathematical induction fundamentals, hypothesis or assumption is also made at the step 2. Example number 1. Basic mathematical induction divisibility. Prove 6 raised to n plus 4 is divisible by 5 by mathematical induction. Step 1. Show it is true for n is equal to 0. 6 raised to 0 plus 4 is equal to 5, which is divisible by 5. Step 2. Assume that it is true for n is equal to k. That is 6 raised to k plus 4 is equal to 5m, where m is element of I. Step 3. Show it is true for n is equal to k plus 1. That is k raised to k plus 1 plus 4 is equal to 5p, where p is an element of I. 6k raised to k plus 1 plus 4 is equal to 6 times 6 raised to k plus 4. It is equal to 6 times the quantity of 5m minus 4 plus 4, where 6k is equal to 5m minus 4 is from step 2. Then it is equal to 30m minus 20. So 5 times the quantity of 6m minus 4 is divisible by 5. Therefore, it is true for n is equal to k plus 1, assuming that it is true for n is equal to k. Therefore, 6 raised to n plus 4 is divisible by 5.
Example number 2. Increasing more than 1. Prove n times n plus 2 is divisible by 4 by mathematical induction if n is any even positive integer. Step 1. Show it is true for n is equals to 2, because 2 is the smallest even number. 2 times 2 plus 2 is equals to 8, which is divisible by 4. Therefore, it is true for n is equals to 2. Step 2. Assume that it is true for n is equals to k. That is, k times k plus 2 is equals to 4n. Step 3. Show it is true for n is equals to k plus 2, because even numbers increase by 2. That is, k plus 2 times k plus 4 is divisible by 4. K plus 2 times k plus 4 is equals to k plus 2 times k plus k plus 2 times 4 equals 4m plus 4 times k plus 2 by assumption at step 2 equals 4 times m plus k plus 2, which is divisible by 4. Therefore, it is true for n is equals to k plus 2, assuming that it is true for n equals k. Therefore, n times n plus 2 is always divisible by 4 for n in even numbers.
Step 3. 2 indices. Prove 5 raised to n plus 2 times 11 raised to n is divisible by 3 by mathematical induction. Step 1. Show it is true for n is equals to 0. 0 is the first number for being true. 5 raised to 0 plus 2 times 11 raised to 0 is equals to 3, which is divisible by 3. Therefore, it is true for n is equals to 0. Step 2. Assume that it is true for n is equals to k. That is, 5 raised to k plus 2 times 11 raised to k is equals to 3m. Step 3. Show it is true for n is equals to k plus 1. That is, 5 raised to k plus 1 plus 2 times 11 raised to k plus 1 is divisible by 3. 5 raised to k plus 1 plus 2 times 11 raised to k plus 1 is equals to 5 raised to k plus 1 plus 2 times 11 raised to k times 11 is equals to 5 raised to k plus 1 plus the quantity of 3m minus 5 raised to k times 11. 2 times 11 raised to k is equals to 3m minus 5 raised to k by assumption at step 2. is equals to 5 raised to k times 5 plus 33m minus 5 raised to k times 11 is equals to 33m minus 5 raised to k times 6 is equals to 3 to the quantity of 11m minus 5k times 2, which is divisible by 3. Therefore, it is true for n is equals to k minus 1, assuming that it is true for n is equals to k. Therefore, 5 raised to n plus 2 times 11 raised to n is always divisible by 3 for n greater than equal to 0.
Mathematical induction, inequality proofs. Mathematical induction inequality is being used for proving inequalities. It is quite often applied for the subtraction and or fitness using the assumption of the step 2. First example, basic mathematical induction inequality. Prove 4 raised to n minus 1 is greater than n squared, where n is greater than or equal to 3 by mathematical induction. Step 1. Show it is true for n is equals to 3. Left hand side is equals to 4 raised to 3 minus 1 is equals to 16. Right hand side is equals to 3 squared is equals to 9. Left hand side is greater than right hand side, therefore, it is true for n is equals to 3. Step 2. Assume that it is true for n is equals to k. That is, 4 raised to k minus 1 is greater than k squared. Step 3. Show it is true for n is equals to k plus 1. That is, 4 raised to k is greater than quantity k plus 1 squared. On the left hand side is equals to 4 raised to k is equals to 4 raised to k minus 1 plus 1 is equals to 4 raised to k minus 1 times 4 is greater than k squared times 4 is equals to k squared plus 2 k squared plus k squared is greater than k squared plus 2k plus 1 is equals to quantity k plus 1 squared is equals to right hand side. Left hand side is greater than right hand side. Using the assumption of 4 raised to k minus 1 is greater than k squared and 2k squared is greater than 2k and k squared is greater than 1 for k is greater than or equals to 3. Therefore, it is true for n is equals to k plus 1, assuming that it is true for n is equals to 3. Therefore, 4 raised to n minus 1 is greater than n squared is true for n is greater than or equal to 3.
Mathematical induction inequality using the difference. It is quite often used to prove A is greater than B by A minus B greater than 0. Prove n squared less than 2 raised to n for n greater than equal 5 by mathematical induction. Step 1. Show it is true for n is equal to 5. Left hand side is equal to 5 squared is equal to 25. Right hand side is equal to 2 raised to 5 is equal to 32. Left hand side is less than 2 right hand side. It is true for n is equal to 5. Step 2. Assume that is true for n is equal to k. That is k raised to 2 less than 2 raised to k. Step 3. Show it is true for n is equal to k plus 1. That is quantity k plus 1 squared less than 2 quantity k plus 1. Right hand side minus left hand side equal 2 raised to k plus 1 minus quantity k plus 1 squared equals 2 times 2 raised to k minus quantity k squared plus 2k plus 1 greater than 2x k squared minus quantity k squared plus 2k plus 1 equals 2k squared minus 2k minus 1 is equals quantity k minus 1 squared minus 2 greater than 0. 2 raised to k plus 1 minus quantity k plus 1 squared greater than 0. K plus 1 squared less than 2 raised to k plus 1. Therefore, it is true for n is equal to k plus 1 assuming it is true for n is equal to k. Therefore, it is true for n is equal to k plus 1 is true for n greater than equal 5.